Welcome back. This is another proofs lecture. We've now reached the next topic in the induction chapter. We've talked a lot about ordinary induction so far. Now it's time to move on to another version of induction called strong induction. Sometimes it's also called complete induction. Our goal is still to be, we're going to try to be proving a universal statement, P of n is supposed to hold for all, let's just say positive integers n for this first part of this lesson. And before I get into the details of what we do formally, let's go back to this domino picture that we saw before that gave us some intuition for ordinary induction. And just recall, in ordinary induction, okay, well, you prove P of 1, you do the base case. Briefly, you fix an n, you assume P of n, and you prove P of n plus 1. And this part's the induction step. All right, and the idea, we saw the dominoes falling down, like if P of 1 is true, that means the first domino falls down. And in general, by the time you get over here, the idea is that the statements are somehow being proved in order, in some sense. And by the time you get around to trying to prove P of n plus 1 and make that domino fall down, you've already gotten to n earlier, so it's may as well assume you already have that domino having fallen down. Okay, that's the intuition anyway. And if you think about the sequence of statements that are being proved in this cascade with the dominoes falling from left to right in order, you might realize that actually, by the time you get here, there's even more stuff that's already happened. Like not just the previous dominoes falling down, but all of them. All dominoes prior to this one will have fallen down before you even worry about whether this one is going to fall down as well. So that's the idea of strong induction. That in the induction step, and we'll write the full details in a moment, but in the induction step, you can assume something even stronger to help you complete the step. Here we just assumed one instance of the statement. We assumed P of n. But we'll actually be able to assume all of the statements prior to n plus 1. P of 1, P of 2, dot, 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 P of n. We might as well say that all of those are known at the time when we're trying to prove P of n plus 1. And so, okay, we never needed that before, but it often happens, and we'll see some examples soon, that if you have a recursive definition where the next value of the thing you're defining, it might depend on more quantities than just the most recent one. It might go back further. And then you might have to have this extra information in your hand in order to deal with those recursive definitions. We'll see that again shortly. So, all right, so that's the idea. That's the intuition for what the strong induction is. You're making the induction hypothesis stronger to help you, to give you even more information to help you prove the next instance of your main statement. All right, but now let's officially give the template for proving something. And I don't want to just limit it to 1, starting at 1. Like we did before, you can start at any positive integer. It doesn't have to, just any integer, right? So let's write down this template. So strong induction proof template. All right. So what's the goal? What is this template used for? We're trying to prove a universal statement for all n in the integers greater than or equal to b P of n. That's what we want to prove when we use this template. And we'll start off by saying we use strong induction, sometimes called complete induction. All right, and all right, it might look a little bit strange, but so what we're going to do, we're going to fix an arbitrary integer. Let's call it n naught for a moment, greater than or equal to b, to emphasize it's one particular constant value of n. Okay, and then, so now we have to do this assumption here. This is the part that's going to be a little bit more elaborate. Assume, all right, what do we assume exactly? So here I had p of 1 through p of n, because I'm starting at 1. In general, we're going to be assuming we have to start at b, for one thing. And I'm also going to change the indexing just a little bit so that the next one that's about to be proved, I'm going to call that p of n naught, not n naught plus 1. Okay. So let me just write it, and then we can think about what I'm writing. So for all integers m in the range, all right, starting at b, so b is less than or equal to m, and then m is going to be strictly less than n naught, and we're going to assume that p of m is true. Okay, so we're going to assume p of b, and p of b plus 1, and p of b plus 2, dot, 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 all the way to p of n naught minus 1, essentially. All those get assumed. And then the goal is to prove p of n naught is true. Okay. And in principle, that's the end of the template. And you might worry that, oh, wait a minute, didn't I forget the base case? Okay. So in the ordinary induction, we have the base case, right? And I didn't mention that here. I just sort of leaped into this induction step with this new strong induction hypothesis. But what happened to the base case? Okay. So it turns out, I've phrased this in a very crafty way, the base case is included in this step. Okay. So like one of the values that n naught could be, maybe n naught is b, the smallest value that you're interested in which case there aren't any m's in the range between b and b exclusive. You have to be less than, there's nothing in there. So this assumption isn't actually assuming anything for that particular n naught, and you still have to prove p of b is true, basically without any extra information. So it's hidden in there, but we should explicitly remark to complete star, we call this goal here star, we very often do need proof by cases where there are some special cases, one or more special values of n naught at the beginning, like b, sometimes b plus 1, b plus 2. There might be several base cases, actually. So we often need to look at n naught equals b separately. And perhaps some other small values as well. And so those, you could certainly think of those as being like the base cases perhaps, there might be more than one, of the strong induction proof. But as phrased, it's not really there officially. And then you can say, well, how do I know whether they're going to be, right? And the way you basically know is that the base cases or base case of your recursive definition that's appearing in your statement will sort of guide you into what the base cases of the proof are going to be. So let's mention that as well. Base cases of the recursive definitions often suggest the base cases of a strong induction proof or an ordinary induction proof. And we'll have an example in just a moment of how that works. The other little technical comment is I haven't really justified why this is a legitimate way of proving this statement, other than this domino thing, which I hope is somewhat believable. But dominoes don't prove anything, right? So you might think, okay, do I need another axiom? Do I need a strong induction axiom that says, doing all this stuff gets me this goal? And the answer is no. We already talked about the ordinary induction axiom, and it's actually possible to prove from that axiom that this method does in fact prove this statement. So you're proving that the proof template works in general. That, however, is a little bit technical, and certainly in this time-compressed version of the course, we're not going to go through that here, but it is possible. You can look in the book for the details of that if you really want to see it. Okay? But our emphasis here is executing strong induction proofs, not worrying about exactly why it's justified in a formal way. So let's turn to some examples. And the main difficulty with strong induction is that the assumption is more elaborate. It takes a little while to get used to this new phrasing of the strong induction hypothesis and exactly how you get to use it. But let's take a look at an example. Sample proof, which also has a definition in it. This is another recursively defined sequence. We saw one of these before. So define A0 equals 3, A1 equals 8, and AN is 4 times the difference, AN minus 1 minus AN minus 2, for all integers n at least 2. So recursive definition, this one has 2 base cases. I give you A0, A1, and you need thing, because this is going to, for AN, you have to go 2 back to get the next one. And just as an example of this calculation, so like, what's A2? It's 4 times A1 minus A0, so 20. And A3, now you can get A3. So A3 is 4 times A2 minus A1. So this is the previous thing and the one before that. So you take 4 times 20 minus 8. So you get 48, etc. Just as an example of the recursion. But what I want to do here, like the one we did before, is you want to actually figure out, I mean, maybe if you generated a whole bunch of these numbers, 3, 8, 20, 48, you could generate even more, and maybe you'd eventually see the pattern in this sequence of AN. I'll just tell you the pattern. It might not be so easy to guess it, and we're going to try to prove it. I claim that for every n integer greater than or equal to 0, AN is given by the non-recursive explicit formula n plus 3 times 2 to the n. And maybe we can just check, see if I made an arithmetic error. So if n is 2, for instance, it's 5 times 2 squared. 5 times 4 is 20. If n is 3, I get 6 times 2 to the 3. 6 times 8 is 48. So these seem to be right. But how do I know it's right for every n? Okay. You have to have a proof. You have to have induction. All right. Proof. In fact, and the clue here, in this problem, to get AN, by definition, you have to go 2 back, not just 1. So just ordinary induction would not be enough here. It's not powerful enough. We use strong induction. On here. All right, so we can follow the template. We'll get to these so-called base cases, but we can actually launch right into the main thing first, this sort of induction step. So let's do that. So let's fix an arbitrary integer. So what's b? B is 0 here. We're starting at 0. So we're fixing an integer n greater than or equal to 0. I'll call it n, not n naught, because there's too many subscripts otherwise. Okay. And now we get to this assumption, which kind of gives people trouble until you get used to it. Just copy it down directly with substituting in for b. B is 0. We're assuming for all integers m in this range, p of m is true. And I'll even rephrase that as an if-then. I'll say if m is greater than or equal to 0, but less than n, this n I just fixed, then p of m is true. Now, what's p of m and p of n? P of n is this statement in the box here. Okay, this guy here. And therefore, p of m is this same statement with n replaced by m. So we get to assume for a whole bunch of m's, a whole bunch of them, that am is m plus 3 times 2 to the m. Like every value of the subscript of the index of the sequence going up to but excluding n, we can assume we already know that. And then the goal, again, it looks a little different from ordinary. I don't have n plus 1. I just have n here. So now the goal is this guy with n, the particular n that I fixed. We have to prove that. Okay. Now, you might have been tempted to say here that I'm assuming, right here, I'm assuming p of 0 and p of 1, p of 2, ... p of n minus 1. That's basically what's happening. The reason I don't write it that way is because of this ... this ellipsis we're not supposed to be using in a completely formal, rigorous thing. And by phrasing it as an inequality, I mean, these are the m's I'm getting to use. And these are the ones that I get to assume are true. But it's a little bit safer to phrase it that way. But in just a minute, as you'll see, I'll use this known assumption for n minus 1, and n minus 2 for that matter. Okay. But before that, we have to deal with some base cases. Okay. So because, and here's where the definition helps us see what's going to happen. There's really 3 things. Here's a 0, here's a 1. Here's the general term for 2 or higher. N in the proof could be as low as 0. Okay. And so what I intend to do here is say, well, n is either 0 or 1 or greater than or equal to 2. We know that. It's an integer, at least 0. So those are the things it could be. All right, hopefully that bell was you could hear it, audible, I guess. And when that bell rings, when you have a known or statement, you're going to think proof by cases. Proof by cases. And these cases are, in fact, what we were calling the base case. Now there's going to be more than one of them that correspond to the base cases of this recursive definition. Let's call the first case, case 0. In case 0, let's assume n equals 0. And this is still the goal in all the cases. I'm trying to prove this instance of the formula. And then here, it's the instance I need is that a0 is 0 plus 3 times 2 to the 0, substituting a 0 n for n everywhere it appears. Okay? And how do we do that? Like other base cases in the past, we can calculate both sides, see if they're equal. Left side a0 is 3 by definition. the right side okay, so we have to go through a little bit of arithmetic here. Here's the right side. So 0 plus 3 is 3. 2 to the 0 is 1. We get 3. So the two sides are equal. So that worked. Of course, for any small value of the subscript, you can just do it and see. And you're in fact required to do that as part of the base case. That was the first base case. Let's go on to the next one. 2 to the m, all right. Let's call this one case 1. Assume n equals 1. Prove, and here's the goal, still the goal, but now n is 1, so we have to prove a1 is 1 plus 3 times 2 to the 1. And we just do the same thing. Let's say it like this. No, a1 equals 8 by definition. And on the other hand, 1 plus 3 times 2 to the 1 is 4 times 2, which is 8. So the two sides are equal. Great, so we did that. And now sort of the main case that's not the base case, it's like the actual induction step, is this case, called case 2, or case greater than or equal to 2 if you want. Assume n greater than or equal to 2. And see if we can prove the goal. Here, this is still the goal in all the cases. an equals n plus 3 times 2 to the n. All right, but now we have to do something different. What we have to do now is use, because n is at least 2, now we're in this part of the recursive definition, and we're actually going to have to calculate with this guy. Okay, we'll have a chain proof. We'll go from here to there, and the first step of the chain will be right here. Before we do that, we got to worry about this stuff. Okay, so we have an minus 1, an minus 2. What are we going to do with that? Okay, and that's where this is going to come in. Okay, we have to use this assumption somewhere. I haven't used it yet. And we have to use it in the right way, okay? And so one of the things, this is something that's true for all m in this range, okay? You've got to pick the m's you want in this known universal statement to get you to here. So let's first do that. So I'm going to say, so take a look at this. Let m equals n minus 1. Use that value of m. Is that allowed, by the way? Yes, because n minus 1 is less than n, and greater than or equal to 0 because n is at least 2. So let's make note of that. N is at least 2 in this case, and therefore n minus 1 is at least 1, actually, but it's certainly greater than or equal to 0. And let me call this star. Assumption or induction hypothesis star tells us, among many other things, that n minus 1 is n minus 1 plus 3 times 2 to the n minus 1. And what I did, I just replaced the m. Everywhere I saw an m, I put n minus 1. And I got a formula for this. Okay. And then, well, I'm going to do the same thing with this one. That you can get even more information out of this. So you can let n equals n minus 2. And again, you've got to worry, is it going to really do that? Well, n minus 2 is strictly less than n, surely. But here, this 0 part only works. 0 less than or equal to n minus 2 only because n is greater than or equal to 2. So you couldn't have done this. That's why these other cases, one of the reasons the other cases were needed, because you couldn't go back like that until you hit 2. Okay. So then, star tells us that a(n minus 2 is n minus 2 plus 3 times 2 to the n minus 2. Okay, so that's all preparation for the main chain proof. Now we're going to do this guy. So we can say compute or something. We know, whatever. What do we know? So a(n is supposed to be equal to this, but we don't know this yet. Only thing we know about a(n, keeping in mind that n is at least 2 in this case, therefore it's here. Here's the definition of a(n. a(n is 4 times a(n minus 1 minus a(n minus 2 by definition. But again, noting very carefully that that had to have greater than or equal to 2. That's why 0 and 1 had to be separate. I couldn't have said those for that if n was 0 or 1. Okay, so get that. Then, if I can number these 1, 2, I can keep going by putting in these guys. So n minus 1 plus 3 times 2 to the n minus 1 is what this is, minus, maybe I should like circle these guys, help you see them. Now I've just obliterated everything, but oh well. Try to fix that. All right, sorry about that. All right, so anyway, so now minus a(n minus 2, so now I have to take this guy and copy it in. All of that's being multiplied by 4. So this is true by 1 and 2. All right, let's move here just to have some more room. Now we're going to start cranking out some algebra. So what do I get? So I have n plus 2 times 2 to the n minus 1 minus, and I get n plus 1 times 2 to the n minus 2. Okay, and let's see, so 4 is 2 squared, and I can bring that over, so it's like n plus 2 times 2 squared times 2 to the n minus 1. And here, minus n plus 1 times 2 squared times 2 to the n minus 2. All of these steps are by algebra, of course. I've also I distributed the 4. 4 times this minus 4 times that. So and written 4 as 2 squared. So there's the 4. Okay. And all right, remember we had laws of exponents, because we proved that last time. So now I can combine these 2's a little bit. So n plus 2 times 2 to the sum of the exponents. So that's actually 2 to the n plus 1. And here it's minus n plus 1 times 2 to the, and the sum of these guys is 2 to the n. I should be writing reasons, but this is all algebra, right? And here it's laws of exponents as a reason for that. Don't want to run out of room right at the end. But anyway, oh, and you know, so now we can factor a 2 to the n out. And we still have 2 to the 1 times this. And here I just have 2 to the n times this other stuff being subtracted. Again, I think you can see it. We'll find out at the end if you could really see all the way down here. Almost there, though. So equals 2 to the n, and this is going to be 2n plus 4 minus n minus 1, distributing the minus. And then finally, when you do this, 2n minus n is n, 4 minus 1 is 3. That's what it is. Now, what was it supposed to be? That's what it was supposed to be. Our goal was to get to that. Again, to summarize, don't you get lost in the algebra at the end. The main thing was we had this, and we were able to substitute for both of these terms using this induction hypothesis. We did that here, and then we just grinded through a bunch of algebra to get until it finally turned into something, and it was exactly what we needed. So that's the end of the entire proof. All right, so a little bit elaborate. That's the nature of these things, but nothing we couldn't really handle. I do want to do one more. It looks like I'm at 30 minutes now, but this next one shouldn't be. Well, we'll see. 10 minutes or so. We'll see. All right. So here's a very different kind of problem that we can use induction for. Another proof. Prove for all integers n at least 12, there exist non-negative integers a, b, such that n has the form 7a plus 3b. And this actually has an interpretation in terms of stamps. It's like you're trying to send an envelope that costs n cents postage, and is 12 or more, but you only have 7-cent stamps and 3-cent stamps. And you're supposed to somehow use those stamps, if you can, to get exactly n by putting a bunch of stamps on the envelope. You're not required to use either one. You have 0 of them, but you're not allowed to have a negative number of the stamps. That's what makes this tricky, is that A and B have to be greater than or equal to 0. Okay, and in particular, if you're saying, well, why 12? Like, where'd that come from? If you think just for a second about n equals 11, how would you do that, right? It's not a multiple of 7. It's not a multiple of 3. So you can't just use all 7s or all 3s to get to that. And so you'd have to use at least one. And so maybe you think, okay, I'm going to use a 7-cent stamp. But then you get 4. And certainly 4 is not reachable using 3 and 7 only. Okay, so that doesn't work. And then you can't use 2 7s because you're already too big. So basically, you can see, I didn't write all the details, but you can see that's impossible. You cannot write 11 in this way. Okay, and so now you might worry about, well, what about 12? I mean, and that's what the proof's going to show. It's going to work from 12 on. So proof. And it might not be evident now, but strong induction is called for here. Strong induction on n. So we'll follow the template. We'll fix an n. Let n be a constant integer with n at least 12. Just for some variation here, I didn't say fix, but this is what it means when I say fix. It's constant. Okay, and then we have to prove, and in this case, the inside statement has quantifiers. There's other variables that are quantified. That's allowed. So this whole thing here is p of n. All right. Well, okay, so I jumped ahead a little bit. So that's gonna be the goal. But before that, I'll just sneak it in here. I really should have said it here. We can assume, what do we get to assume? That basically this statement is true already for every value of the variable n less than this n that I just fixed. Okay. So let's say that carefully. For all integers m in the range, and here's where we have to be careful, it's not just everything less than n. It still has to be bigger than 12 or equal to 12. just saw that 11 doesn't work. So the range is 12 less than or equal to m is less than n. And what do we assume about it? Well, this statement, that we have to be careful, because I'm going to replace the n by m, but the a and the b, just for safety, let's not use the same letter. It's probably not the same a and b that work for n. There's going to be a different a and b that work for m. Okay, so I'll change the letters in the assumption. It doesn't change the meaning. It's just to avoid a notation conflict. That sometimes happens. And again, you can say it in English as well, without necessarily quantifiers, that m can be written in the form. If you use 7-cent stamps and 3-cent stamps to get m. Okay, but the number that you need, which I'm calling C and D, the number you need for m is probably not the same numbers that you use to get n. So let's use other variables for that. Okay, so there's my induction hypothesis. Now we come to the sort of hardest line in the proof. We know, what do we know? I claim that we know that n is equal to 12, or n is equal to 13, or n is equal to 14, or n is at least 15. All right, that's certainly true. Remember, n is at least 12, integer. But the thing that's hard about this is, like, why did I know to write that? Okay, and well, for now, I'll just say, because I did the proof before, and I know, but just trust me for a second. Well, we'll see later why. At the end of the proof, we'll retroactively see. But for now, just accept that we've said this. And that this is going to trigger, when you have an OR statement with these cases, right? And basically, another way of saying it is, I'm just about to do some base cases for you. Three base cases. I'm going to treat several small values of n just directly, okay, without even using the assumption. So what if n is 12? Let's call this guy star here. When you're proving star, which is an existent statement, you have to choose the a and the b. And if you have a particular n, let's even write it. So prove there exists a, b, non-negative integers, such that 12 is equal to 7a plus 3b. All right, and okay, so you can just look at that and figure out pretty quickly that you can use a equals 0, b equals 4. These are greater than or equal to 0, and integers, of course, and it works, because 12 is equal to 7 times 0 plus 3 times 4. All right, and 0 is allowed for these things. Just negative is not allowed. All right, so that's what you're going to do. Case 2, let's see if this... No, it's not blocking it. Okay, I was worried the chair was blocking it. N equals 13. All right, and I won't keep writing the statement. As I said, now let's say 13. How do you do that? 13 equals 7a plus 3b. And here you just sort of try stuff, and eventually you see, okay, 7 plus 6. So if we choose a equals 1 and b equals 2, which of course are in the universe that you're allowed to use, namely z greater than or equal to 0, and that's going to work. So calculate or compute 7a plus 3b, 7 times 1 plus 3 times 2, 7 plus 6 is 13, which is equal to n. So it works. Okay. Let's see, so get rid of this. Case 3, n equals 14. And I'll just say it briefly. And so just looking at that, you can see that you can do a equals 2, b equals 0. etc. I won't write all the details there. It's greater than or equal to 0, and it works, all that stuff. 7 times 2 plus 3 times 0 is 14. All right, so now, that's fine. Now for the main case. Case 4. Because, you can do lots of n's this way, but you're not going to do infinitely many n's one at a time. Eventually, you have to do a general case. Assume n is at least 15. And try to prove star. The goal right here. Okay, and so the thing about star, and this proof really, is that we haven't used the induction hypothesis yet. Okay, and this is the crucial observation about this problem. That suppose I had n, this big number, making posters for n, and I'm contemplating how I'm going to do it. Well, I have to use one of these stamps, probably both, maybe not, but we've got 7 cents, we've got 3 cents. What if I put a 3-cent stamp on there? Well, now I only need to change for n minus 3. Okay, and well, that's less than n. So if I've already solved everything less than n, and I look at n minus 3, well, that's something I could do here. I think, but the trouble is, wait. So there's also this guy. So the idea is I want to let m equals n minus 3. That's the intuition. By using one 3-cent stamp, and then recursively solving the rest, or inductively. Only trouble with that is, okay, n minus 3 is less than n, but it's also got to be greater than or equal to 12. Because that's the range. Remember, 11 wasn't allowed. All right, and see, for that to be true, we have to actually have n is at least 15, which it is. But that's why, now you can see, this is why I did this business over here. It's treating these guys separately and then saying, okay, 15, greater than or equal to 15. Okay, because I foresaw that this would happen. Okay, now this was the idea, how do we write this out? I'm going to say, if we call this guy double star, in assumption double star, let m be n minus 3. And again, this is a provisional assumption. It's not every single m and everything. It's just these. Okay, so I have to notice this is p because n is at least 15 in case 4. That's what we assumed about n. We do have 12 is less than or equal to n minus 3, which is certainly strictly less than n. Also in an integer by closure, if you're worried about that. N is an integer, and so on. Okay. So, because the condition was met, I can conclude this guy, that therefore, there exist C and D, non-negative integers, and now m is n minus 3. And so this is the idea that I've recursively, inductively solved a smaller instance of the same problem. Not n minus 1, but n minus 3. And now, why is that? Why was it 3? Because it's like using a 3-cent stamp. So now this is known. As part of the induction hypothesis, I can manipulate the thing that I know by let's add 3 to both sides. See what we have about n. So n then is 7c plus 3d plus 3, moving the 3 over. But that 3 can be absorbed into this. You can factor. And now, so we have to prove star. We have to prove an existence statement. We have to choose A, choose B. But based on what we have here, this is known now. This is known. We can see what to do for choosing the A and the C. We're going to choose A and the B. We're going to choose A to be C. and we're going to choose B to be D plus 1, and then note that what we just said above, which is known, n is equal to 7a plus 3b by above. So we've almost done it. You should think for a second, what have we not done? What's left? And the answer is that the last thing we have to do is the thing we just chose in the universe that it needs to be in? Well, A is a non-negative integer because it's equal to C, and C is a non-negative integer. And the more interesting one is B. B is an integer greater than or equal to 0. Because D is. But therefore B, which is D plus 1, it's actually even greater than or equal to 1. It's certainly greater than or equal to 0. And it's also still an integer by closure of integers under addition. Okay. So now we have proved star for n in all cases, including this hard case 4, which was like the induction step here. So we did it. All right, so again, the main intuition was if we could put a single 3-cent stamp down and get us from n down to n minus 3, solve that using the induction hypothesis, and then put the 3-cent stamp back in, that's what's happening right here, to go from the smaller solution to the one we need. That's essentially what happened. But again, the logic, there's all these subtleties, right? Because, if you went too small, you would get to 11 or something you couldn't do. And that's why these 3 base cases had to be treated separately. All right, so this one was a little long, but worth it. All right, so that's the end of this one, and we'll talk more about strong induction in the next lesson. Goodbye.